Okay, so in this video we will see the calculation of the sample size for equivalence test, one mean and two means. So let's say that you are manufacturing tablets with a target amount of 250 milligrams, and you have introduced a new manufacturing process, and we want to show that the new system is equivalent to the old system. How many tablets do we need to analyze these in order to show that both systems perform equally? Presume that the variance of the manufacturing process has to be estimated from the data, and we want to detect departures from the mean of at least 2.5 milligrams that we will call delta, small delta, and the standard deviation of the process is 3 milligrams. We want to have a power of 90% if the difference is larger than 5 milligrams, and we will call it capital delta. And we fix here the confidence level. Okay, so now the alternative goes here, goes into 250. We want to show that both are equivalent. Remember from the first lecture that we can never accept the null hypothesis, so we have to put the equal sign in the alternative, and this seemingly innocent change will change a lot the way to calculate. Okay, so the hypotheses are that the alternative is that they cannot be exactly equal, so that is why we have this tolerance that is a small delta. So our alternative is that the difference between the true mean and the expected mean is smaller in absolute value than this tolerance, and the null hypothesis is the opposite, it is larger. But you may remember from your algebra courses that an absolute value is translated into branches. One is that mu minus mu 0 is smaller than delta, so the positive side, and the negative side is that mu minus mu 0 is larger than minus delta. So this is the alternative, and the opposite, the null hypothesis, is that either it is larger than delta or it is smaller than minus delta. So actually, when you look at these two pairs, and or this pair and this pair, you see that they have exactly the same condition except for the sign. So this one is larger than minus delta, this is smaller than minus delta. So this is a superiority, a non-inferiority test, and this is a non-superiority test. So actually we have split our hypothesis, original hypothesis, into two hypotheses, two one-sided hypotheses. So this technique is called toast, that is two one-sided tests. So we have decomposed something that depends on the absolute value onto two one-sided tests, and then we will have two tests to check, so this one and this one. And now these we already know how to do that, because it is they are similar to the cases that we have already. But here is an implication of that. So in the significance test, that is the one that we typically do in biomedical research, the mean, for instance, this is the example of the tablets that the engineer that had to stop the machine if the machine was not working correctly. So the null hypothesis is that it is working correctly, so the mean should be 250. If he sees or she sees a mean of 20 tablets that is outside this area, these blue areas are alpha half, so having a probability of alpha half, then the machine should be stopped. And And so the null hypothesis is this one, is at the middle, and then if you have deviations, you stop it. You reject the null hypothesis. Here, you have two null hypotheses. One is centered at mu minus delta, and the other one at mu plus delta. So you have one at mu minus delta, the other one at mu plus delta. And they are one-sided. They are one-sided because you only have to look at one. We are using these larger or equal signs. So we reject the null hypothesis if the value is larger than here. We reject this null hypothesis if the value is smaller than here. So now we have two hypotheses to test, and if we reject the first hypothesis and we reject the second one, then what we have to accept is that the new machine is working at 250 with a mean of 250 with this tolerance of delta. Okay, so now we know how to do that because we have the formulas for the noun, for the hypothesis test. Each one of these ones we know how to compute, and we have the formulas with n when the sigma is noun, when the sigma is unknown, and you have to estimate from the data. And what is interesting here is the way to normalize the effect size. So the effect size is not delta divided by sigma, but delta, so the difference that we want to detect, minus the tolerance divided by sigma. So in our example, we had 5, so we wanted to have a power of 90% to detect changes of at least 5 milligrams, and then this was the tolerance divided by 3. This is a relatively simple case with only 16 tablets. We can show that. What is interesting of this example is that something that we have moved, if we move the equal sign from the null to the alternative hypothesis, now we have two tests, and one on the left, one on the right. We have to define a tolerance, and the calculations are not much more difficult, but the way that we have reached those calculations, it is rather different. Okay, so what happens if we want to compute the equivalence of two means, not one mean? So let's say that you have two different drugs and you want to show that they are bioequivalent. So the mean effect of the when you are taking the reference drug, the mean diastolic blood pressure is about 96 milligrams of mercury, and then the experimental drug is presumed to be similar. The population variation, so sigma, is 18. The two drugs are supposed to be similar if their difference is smaller than 20%. Again, this is the kind of if it goes beyond 20%, then they are not different anymore, and you want to detect that with 5% of confidence level and 90% of statistical power. So the minimum detectable difference, this is the tolerance of our previous example, is 10 millimeters. So again, our equal sign is now in the alternative, so we will have two tests, one on the left, one on the right, and it is similar to what we had before in the cases of the significant tests, the significance tests, that simply changing delta by the absolute value of delta minus the minimum detectable difference. And where we had alpha half, we had to put alpha. So now the way to normalize would be this one. So the minimum or the change that we want to detect, what is the minimum detectable difference divided by the standard deviation, so this is 0.5, and then all the rest is similar. So we will use the easy case in which the two groups have the same size, and then when you solve for n, you have this equation, n is equal to 83. So let us stop here and separate the other topics into different videos.